Good day, students. The fourth lesson in Module 6 is about stoichiometry. So, what is stoichiometry? It is derived from the Greek word stoichion, which means element, and metron, which means measure. So, stoichiometry is a quantitative study of the reactants and products in a balanced chemical reaction. So, we use a balanced chemical equation here. When we say quantitative, we are dealing with measurements. Okay, so we use stoichiometry so as to calculate the amount of reactants and products in a chemical reaction. So here, this is what we use, no? The schematic diagram, so we can compute for the mass of our reactant or product. So in the first step here, if we want to convert mass to mole of the same compound, for example, we have compound A. If we want to convert mass to mole of compound A, we will use smaller mass. We have actually taken up this, no? How to convert mass to mole and vice versa of a compound, a same compound. So in this case, we use smaller mass of that compound. Now, if we want to convert mass of compound A of one compound to another compound, in this case, we will now use the balanced chemical equation. But first, we have to convert mass of compound A to compound A, mole. After that, we will use the mole ratio of A and B in the balanced chemical equation so as to convert the mole of compound A to compound B and vice versa. Okay, so if you want to convert mole to mole of one compound to the mole of another compound, you use the mole ratio of the two compounds from the balanced chemical equation. When we say mole ratio, they are the coefficients of the compounds in the balanced chemical equation. So it's important that your equation is already balanced before you use the coefficients or the mole ratio of the compounds. Now, once you have the mole of compound B, you can now use the molar mass of compound B to convert that mole into mass. Okay, so in converting mass to mole of the same compound, we only use smaller mass of that compound. But if we want to convert mass or mole of one compound to another, we now use a balanced chemical equation. So let's have an example. The following reaction is used to extract gold from pretreated gold ore. So we have this equation. Now let's see first if we now have a balanced chemical equation. On the left side of the equation, we have 2 moles of gold. We have 2 times 1. On the right side, we also have 2 moles of gold. For zinc, we have 1 on the left side and 1 on the right side. For carbon, we have 2 times 1 is 2 multiplied by the coefficient here. So we have 2 times 1 is 2 times 2. We have 4 on the left side. For the right side of the equation, we have 4 times 1 times 1 in the coefficient. We still have 4. So we have balanced number of carbon atoms in the equation. Lastly, for nitrogen atoms, we have 2 times 1 is 2 times 2, we have 4. On the other side of the equation, we have 4 times 1 times 1, it's still 4. Okay, so the equation is already balanced. Now, we can proceed to computing the required in the problem. So first, how many grams of zinc are needed to react with 0.11 mole of this one, gold 2 cyanide? So in the first equation, we are given with 0.11 mole of this. We have to convert that into gram of zinc. Okay, so we have one substance convert to another substance. Of course, we need a balanced chemical equation. How do we do this? In converting mole of gold 2 cyanide to gram zinc, what do we do first? Diba? In the equation, we have gram A, then that becomes small a, then convert to mole B, and lastly to gram B. So in this case, we start with mole A. No? We're already now in mole because the given is in mole. So we have mole A to gram B. In this case, the B is zinc. Okay. Letter B, how many grams of gold can form from 0.11 mole of gold to cyanide? So we have 0.11 mole of gold to cyanide. Convert that into gram gold. Okay, so it's still the same thing. We start with mole A in the general schematic diagram. Mole A to gram B. In this case, the gram B is gram gold. Okay, so that's what we do. Now let's solve first letter A. So we start with 0.11 mole of gold to cyanide. Then to convert, define the equation, we have to convert this first to mole zinc. So we use what do we do? We use the mole ratio of zinc and gold to cyanide in the equation. So in the equation, we have 2 moles of gold to cyanide and 1 mole of zinc. So we have in the what do you call this, conversion factor, this is our conversion factor here, we put mole gold to cyanide in the denominator so that we can cancel this unit, and the mole zinc in the numerator. So next, to convert mole zinc to gram zinc, we will use the molar mass of zinc. So the mass can be found in the periodic table of elements. Here in the conversion factor, we put mole zinc in the denominator so that we can cancel that unit, and the gram zinc in the numerator. Okay, so you can look at this value in the periodic table of elements. So now we cancel mole gold to cyanide and mole zinc. Now the numbers which appear in the numerator will be multiplied, and then that will be the resulting answer will be divided by the numbers in the denominator. Okay, so therefore we have the answer 3.6 grams of zinc. Okay, so this is now our answer for letter A. In the second problem, we are to convert mole gold to cyanide into gram of gold. So again, we will use the mole ratio of gold to cyanide and gold. In this case, we have 2 is to 2. Okay, the mole ratio that we're going to use are actually the coefficients. Okay, the numbers which appear before the chemical symbol of the substance. So to solve that, of course, we start with a 0.11 mole of gold to cyanide, and then we use the mole ratio of gold to cyanide and gold. So we have 2 moles of this and 2 moles of gold. Then to convert mole of gold to gram gold, we use the molar mass of gold, which can be found in the periodic table of elements. Again, we put the mole of gold in the denominator and the gram gold in the numerator so that we can get our desired unit, which is gram gold. So now we cancel the units. The units which can be found both in the numerator and the denominator are all cancelled. Okay, then we multiply the numbers in the numerator divided by the numbers in the denominator, and we get 21.67 grams of gold. Okay, so that's it for the solution in the second question. Now in stoichiometry, we have the so-called limiting reactant. When you say limiting reactant, it is completely consumed in the reaction. So it determines the amount of products that can be formed. Okay. We also have the so-called excess reactant. So this is from the term excess. It's not completely used up in the reaction. So recall these terms. So limiting reactant completely consuming the reaction and determines the amount of products that can be formed, whereas excess reactant is not completely used up in our reaction. So the amount of products that can be formed depends, no, on our limiting reactant. Okay, we have here an example. We have hydrogen gas, and oxygen gas reacting to form water. Okay, in water we have 2 hydrogen for each 1 oxygen. So what happens here, for example, we have 2 of this and we get 1 of the oxygen. We have another one here which combine with here to produce another water molecule. We have another 2 hydrogens or hydrogen gas which combines with 1 oxygen to form another molecule of water, and we have the last hydrogen molecule here which combines with 1 oxygen to produce another water molecules. We have 4 water molecules formed here, and we have the remaining oxygen. So in this case, as you can see, all the hydrogen gases are used up or completely consume the reaction, whereas oxygen we still have remaining, no? So the limiting reactant, the amount of water that can be formed depends on the, in this case, on the hydrogen, no? Because although we still have oxygen available, all the hydrogen are already consumed. So we cannot make any more water molecules. So in this case, hydrogen is the limiting reactant and oxygen is our excess reactant. Okay, so the amount of product is determined by the limiting reactant. Okay, let's have here an example. Lithium nitride, an ionic compound containing the lithium and nitride ions, is prepared by the reaction of lithium metal and nitrogen gas. Calculate the mass of lithium nitride formed from 56 grams of nitrogen gas and 56 grams of lithium in the unbalanced reaction. So we have an unbalanced reaction. Which of the 2 reactants is limiting? Again, we have to use balanced chemical equation. So we have to balance first the equation. So how do we balance the equation? We start with between lithium and nitrogen. Nitrogen has larger atomic number. So on the left side of the equation, we have 2 nitrogen atoms. 2 times 1 is 2. On the right side, we have 1. Okay, 1 times 1 is 1. So what we do is we put a coefficient 2 in here, because when we multiply 2 by 1, we have a 2. Okay, for lithium ion, we have 2 times 3 is 6. On the left side, we only have 1. So we have to add a coefficient 6 in the equation. So we now have a balanced chemical equation. Okay, in the problem again, what do? We have to calculate the mass of lithium nitride formed from, so we start with 56 grams of nitrogen gas and 56 grams of lithium, and we have to calculate how much lithium nitride are formed from each. Okay, so then we have to determine which one is limiting. How do we do this? Once we have calculated the mass of lithium nitride formed using nitrogen and lithium, whichever produced the least, or the not the least, the less amount of lithium nitride, that is our limiting reactant, no? Because although the other reactant can produce more of lithium nitride, since the other reactant can only produce that much, no? So the higher amount of lithium nitride won't be uh, produced, of course, no? Because the other reactant is already used up. So now let's compute how much lithium nitride can be formed from 56 grams of nitrogen gas. So how do we do this? This is from gram to gram, no? So this is gram A, then we convert that to mole A, then to mole B, and lastly to gram B. Okay, So we start first with converting gram nitrogen to mole nitrogen by using the molar mass of nitrogen. Okay, so here we put the gram nitrogen in the denominator so we can cancel that unit, and we put the mole nitrogen in the numerator. If you see your periodic table of elements, the molar mass of nitrogen there is 14. Since we have 2 nitrogen atoms, so 14 times 2, we have 28 grams of nitrogen. Okay, so we're done with this to mole A. Next, we convert mole A to mole B using the mole ratio of nitrogen and lithium nitride in the balanced chemical equation. So in this case, we have 1 mole. Since we cannot see any number here, so that means there is 1. This is 1 mole nitrogen to 2 mole of lithium nitride. So we put the mole lithium nitride in the numerator and the mole nitrogen in the denominator. Okay, so we're here. Lastly, we convert mole lithium nitride into gram lithium nitride, no? By using the molar mass of lithium nitride. So we put the mole lithium nitride in the denominator and the mass of lithium nitride in the numerator. So how do we compute the molar mass? We already know how to do this. We look at the molar mass of lithium in the periodic table, multiply that by 3 since we have 3 lithium atoms. Then we add that with the molar mass of nitrogen in the periodic table of elements. Okay, then you'll get 34.82 grams. So now we cancel all the units that can be found in both sides, no? In the numerator and denominator. Okay, so we have gram nitrogen, mole nitrogen cancelled, and mole lithium nitride cancelled. So what we get now is gram lithium nitride, which is required in the problem. Okay, again we multiply all the numbers in the numerator divided by the numbers in the denominator, and we get 139.28 grams of lithium nitride. Okay, so remember this value. From 56 grams of nitrogen gas, we can produce 139.28 grams of lithium nitride. Now, how about when we use 56 grams of lithium? So we convert that to gram lithium nitride. We will compare, no, how much when we use lithium as our starting material. So again, we convert first gram lithium to mole lithium using the molar mass of lithium, which is 6.94 grams. Again, you can look this value in the periodic table of elements. Then we convert mole lithium to mole lithium nitride using the ratio of lithium and lithium nitride in the balanced chemical equation. So we use 6 mole lithium is to 2 mole of lithium nitride. In this case, we put the mole lithium in the denominator and the mole lithium nitride in the numerator. So we have our 6, this comes from here, and this 2 is here. Then we convert now the mole lithium nitride to gram lithium nitride, again using the molar mass of lithium nitride. So now we cancel the units, and then we multiply the numbers in the numerator and divide that by the number in the denominator. We get 93.66 grams of lithium nitride. Okay, so which one is our limiting? It's lithium. Recall that using 56 grams of nitrogen gas we can form 139.28 grams of lithium nitride. Using 56 grams of lithium, on the other hand, we can only produce 93.66 grams of lithium nitride. Okay, so since lithium can only produce 93.66 grams, lithium is our limiting reactant. No? Although nitrogen can produce as much as 139.28, but since the other reactant used to produce lithium nitride is already used up, is already consumed, we cannot produce this much of lithium nitride. So we can only produce the amount 93.66 grams. Okay, So our limiting reactant is lithium, and the amount of lithium nitrate produced is 93.66 grams. We have here reaction yield. What is actual yield? This is the amount of product that actually forms when the reaction is carried out in the laboratory. Okay, so when you perform experiments in the laboratory, you want to synthesize or you want to produce something, the amount that you produce there is called the actual yield. So it's an experimental value. Theoretical yield, on the other hand, represents the maximum amount of product that can be formed from given amount of reactant. So this is actually, this is the amount formed from the limiting reactant. Okay, so the amount there is called the theoretical yield. So how do we get the so-called percent yield? We have the formula: actual yield divided by theoretical yield multiplied by 100. Again, when you say actual yield, that's the amount that you get during the experiment. When you say theoretical yield, it's the amount, no, formed, or the maximum amount that can be formed from given amount of reactants. It's actually, again, the amount that can be formed using the limiting reactant, no? The one computed pa. So ang actual yield makuha during experiment, theoretical yield computed from the limiting reactant. So let's have an example. Although they were formerly called the inert gases, at least the heavier elements of group 8 do form relatively stable compounds. For example, xenon combines directly with elemental fluorine at elevated temperatures in the presence of a nickel catalyst. So we have this equation here. Is this already balanced? We have 1 mole of xenon in the reactant side, and the product side we also have 1 mole of xenon. And the reactant side, we have 2 times 2, so we have 4 moles of fluorine atoms. On the product side, we also have 4 times 1, so we also have 4 moles of fluorine atoms. So this is now a balanced chemical equation. The problem, or the question is, what is the theoretical mass of xenon tetrafluoride that should form when 130 grams of xenon is reacted with 100 grams of fluorine? Okay, so what we do here is, just like the previous problem, we convert 130 grams of xenon and 100 grams of fluorine into xenon tetrafluoride. Xenon tetrafluoride. Xenon tetrafluoride. Okay, so we compare which one has the less amount that is formed, no? And that amount will be our theoretical mass. Okay, the reactant which produced the lesser amount of this xenon tetrafluoride is our limiting reactant, and the amount formed using that limiting reactant is our theoretical mass. Okay, so what is the percent yield if only 145 grams of xenon tetrafluoride is actually isolated? So again, percent yield is equal to actual yield over theoretical yield times 100. Okay, so we now have a value for actual yield. What we do is we have to compute first the value of theoretical yield, which we get from the amount of xenon tetrafluoride produced from the limiting reactant. So this is what we do first. We have to compute the amount of xenon tetrafluoride produced using this amount of xenon and this amount of fluorine. After that, we compare which one is the lesser amount. That is our theoretical mass. And the reactant which produced that lesser amount is our limiting reactant. Okay? Now, once we have that theoretical mass, we can now compute our percent yield. So, using 100 grams fluorine gas, we now compute the mass of xenon tetrafluoride formed. Okay, first step is we convert gram fluorine to mole fluorine using molar mass of fluorine. So we have 38 grams of fluorine gas is to 1 mole of fluorine. This is the molar mass, no, of fluorine. We put the gram fluorine in the denominator so as we can cancel this unit. This is 38 grams because we have 2 fluorine atoms. So the value of the mass of fluorine you can find in the periodic table of elements, you multiply that by 2 because we have 2 fluorine atoms, no? And you'll get 38 grams. Okay, next step. We convert now the mole fluorine into mole xenon tetrafluoride using the molar ratio in the balanced chemical equation. We have 2 moles of fluorine gas is to 1 mole xenon tetrafluoride. Here we put the mole fluorine in the denominator and the 1 mole of xenon tetrafluoride in the numerator. Lastly, we convert mole xenon tetrafluoride into gram xenon tetrafluoride using the molar mass of xenon tetrafluoride. So you look up the molar mass of xenon, then you add that to the molar mass of xenon fluorine times 4. So you look up the molar mass of fluorine in the periodic table of elements, multiply that by 4. Then the the product will be added to the mass of xenon, and you'll get 207.3 grams of xenon tetrafluoride. Okay, so now we cancel the units. Okay, again, those units which appear on the top and bottom part of the equation, or in these conversion factors, are cancelled. So we have 272.8 grams of xenon tetrafluoride using 100 grams of fluorine gas. Now what about when we use 130 grams of xenon? So we convert first gram xenon into mole xenon using the molar mass of xenon, which is 131.3 grams. Again, we put the mass xenon in the denominator so we can cancel that unit. Next is we convert mole xenon into mole xenon tetrafluoride using the mole ratio of xenon and xenon tetrafluoride. So that is 1 mole of xenon here is to 1 mole of xenon tetrafluoride. Lastly, we convert mole xenon tetrafluoride to mass, to gram xenon tetrafluoride. So using the molar mass of xenon tetrafluoride. So now we cancel the units. Okay, and then we get 205.2 grams of xenon tetrafluoride. So let's recap. Using 130 grams of xenon, we get 205.2 grams of xenon tetrafluoride. And using 100 grams of nitrogen, we get 272.8 grams of xenon tetrafluoride. Okay, so the lesser amount here is 205.2 grams. Okay, therefore our limiting reactant then is xenon. Okay, because it produced a lesser amount of xenon tetrafluoride. Okay, again, although nitrogen can produce as much as 272.8, but then xenon is already used up, no? So we cannot form this much, no? We can only form 205.2 grams of xenon tetrafluoride. So this amount here is our theoretical yield. The amount produced using the limiting reactant is our theoretical yield. So what's next is we compute now the percent yield. The actual yield is already given, which is 145 grams of xenon tetrafluoride. Then our theoretical yield, again, this is the amount produced using the limiting reactant, 205.2 grams. So divide that, multiply by 100, we get 70.6%. So this is our percent yield.